This section talks about power functions, and a power function can be represented in this form: y equals k, which is just some real number, x to a power p. And the p, that power can be any real number. So as we look through these examples here, we see that we have a -5 in front and a 3 is a power. Both numbers are real. So this does represent a power function. And the same for the next one. 7 is a real number, -2 is a real number. We're all good there. At first, it doesn't look like j of x is going to be a power function, but if you think about this, remember the square root of x can be written as x to the 1 over 2 power. Remember, there's a little 2 out here and a power of 1. So again, -8 is a real number, 1/2 is a real number. This is a power function. What is not a power function, though, is this next function. If there had just been y equals x squared, that'd be fine. But with this extra stuff added in, notice our power function only has one term, and that term has to have a real number in front and in the power. If you've got extra stuff or extra terms added in, it is not a power function. So we're next going to look to see what happens when you change the k or the p in the problem. So the first thing we're going to look at is if we're looking at graphs with a positive even power. So we're changing the p here. The k is all going to be 1, but the p is going to be slightly different. So rather than do this by hand, we're going to have our calculator help us out a little bit, kind of speed up the process. So as I look at this and I click on my calculator, I've already typed in, let me show you where that is. Go into graph, yep, and that draws the graphs up. But before I do that, I want to show you what I typed in. So go to y equals, type in x squared, x to the 4th, and x to the 6th. And before we actually look at the graph of this, I want to put the numbers in the table so we can see how they compare to each other. So to do that, the first thing I'm going to go into is table set. So do second window and see where my independent variable, remember those are your x values, is on auto. I want that to be on ask because I want to be able to tell the calculator what values I want to plug in for x, namely -2, -1, 0, 1, and 2. The dependent variable I want on auto. So it's automatically going to tell me what the y value is coming out. Next, go into table. So do second graph. And I can now type in my x values. So I've got -2. And because I put the graphs, all 3 of them in there, see I've got y1, that was my x squared. y2 was my x to the 4th. And if I scroll over, there's y3, which was x to the 6th. So I can now type in -2 to the 6th power is 64. And -2 to the 4th power was my number 16. And then if I scroll over, I can see y sub 1, or -2 squared, was 4. And then I can go ahead and type in the rest of the values. So I've got -1, and it just automatically fills in for all of them. 0, 1, and 2. And then I can fill in my chart. So at -1, everybody's 1. At 0, everybody was 0. And then here it was 4, 16, and 64. Now you can make a rough sketch here on your graph, but if you're using a calculator, you might as well just go ahead and look at the graph of them. So go back into y equals, and I want to look at these sort of as they go in one at a time. The first one I'm going to take a look at is x squared. So if I go into graph, I see that horseshoe shape, right? And then if I light up the equal sign, so scoot it over and then hit enter, it's not only going to show y equals x squared because that one's lit up, but it's also going to show me y equals x to the fourth. So if I graph both of those, I can see the difference between the two. It appears the x to the fourth goes up quicker and is a little flatter on the bottom. And to see that a little closer, I can do zoom in and just hit enter. There's y equals x squared, and there goes y equals x to the fourth. Notice it is a flatter bottom to it, but it goes up quick. So now if I do y to the sixth, I'm going to turn off y equals x to the fourth here. So just hit enter there. And I'm going to compare that to x squared. So there goes x squared. And again, you can see how flat the bottom is and how quickly it goes up. Now, if I want to compare that to x to the fourth, again, just go in, highlight them all three. And there goes in the missing one. All right, so x to the fourth and x to the sixth are looking a lot alike, but x to the sixth is going to go up quicker and have a flatter bottom. Okay. If you stop the video now, fill in the chart on the next page with y equals x cubed and x to the sixth. Take a look at their graphs and then write down what you see in the next example at the bottom of that page there. What do positive even exponents have in common, and what do positive odd exponents have in common? And write down the description you see there. So go ahead and pause the video and finish up the next page. So on the next page, I have filled out the chart, again, by using my graphing calculator and typing in x cubed and x to the fifth, and then having the chart just fill in. And if I graph those, I'll see that x to the fifth goes up quicker than x cubed. X cubed kind of takes its time going up. X to the fifth kind of flattens out a little bit more and then straight up real quick, because at 2, it's already up to 32. Whereas on the x cubed, it's only up to 8. So it's kind of taking its time a little bit more. I didn't draw it in very good, but you get the idea. That 32 is going to be up there. Probably be over a little bit more. What you're going to find is the general shapes of these graphs. If p is positive and even, right, and we noticed our k value was 1, we had sort of a U shape. Both ends were up because like I said, the coefficient was greater than 0, and we had an even powered function. It also had y-axis symmetry. So if you think about that, the y-axis is here, and I had what looked like horseshoe shape that will fold over the y-axis. All of those graphs touched at 0, 0. And as the power increased, we saw that our shape, our horseshoe or parabola type feature or function that rather increased more quickly. And so it kind of flattened out in the bottom but went up quick as that power got bigger. When p is positive and odd, in other words, we had x cubed, x to the fifth, and our k again was greater than 0. So we had 1x cubed, k was 1, the power was odd. Our left side was down and our right end was up on both x cubed and x to the fifth. It had something called origin symmetry. And what I mean by that is if you look back at this picture, opposite quadrants are going to have the same picture in them. That's what origin symmetry means. And then it crossed through the point 0, 0, as opposed to a touch and turn. It actually cut through at 0, 0, our origin. And like the other function, we see that as the power increases, our function rises quickly, more quickly than the smaller powers. So that's something that they both have in common.